Hello, eighth grade. Welcome to the first set of notes of your new note packet, physical changes, properties of matter. This is the second part of that big unit, chemical reactions and physical changes. And so this is the first 7 note pages of the new note packet. One of the things that I think is a little confusing, and I can understand that, is we're going to look more in this unit about how things are physically described. And so we look at the different properties of matter, but we really are looking at the physical properties of matter. So first we're looking at some of the chemical stuff, but now we're looking at the physical properties, and not just that, how things can physically change. And we'll talk a lot about changes of state, and you'll see that in the notes to come. But to get us started, I always like to take a look at a picture here and just get some questions to get us thinking about what we see in this picture. And these are some essential questions to get us thinking about the kinds of things we'll explore in this second half unit, in this set of notes. So one, we see this iceberg floating here. Why is some of the water solid? We have water that's in a solid state. Why is the rest of it liquid? Solids and liquids. Why are they what they are? We'll look into that. This ice, why doesn't it sink? I mean, it's water and solid water, and we have liquid water. Why doesn't the ice sink? Why does it float? Here's another one. If the ice is so cold, we know ice is cold, won't the warm liquid water make the ice start to melt, right? Or wait a minute, maybe the ice is so cold, would the solid ice make this liquid water start to freeze? Why is it one or the other? Won't the liquid make the ice melt, or won't the ice make the liquid freeze? I wonder why that is. And I also like to add this question too. We look at this picture, what are some of the elements that we see in this picture? And I like to think about that. If you want to think about what elements are in the picture, we should think about what chemicals do we see in the picture. There's certainly H2O, so I see some hydrogen and some oxygen. We were just talking a lot about water. Floating around the atmosphere, a little oxygen, O2, floating around there, I can certainly see. What else? Oh, maybe a little carbon dioxide floating around in the oxygen. You can't see it, but it's in the atmosphere there. And assuming this is salt water, a little sodium chloride, Na plus Cl minus, held together with an ionic bond. So I just like, as we go through not just unit, but all the units to come, now we start thinking of things on their chemical level. It's the chemicals and molecules that affect how things can both chemically change and physically change. Which leads us into our second note page here. Okay, so we are talking about changes, but I think how something could possibly change, whether chemically or physically, we describe that as physical or chemical properties. For example, in fact, here, let me do the chemical ones first, because we looked into this before. We had just gone through doing some chemical reactions. How things change chemically could be one, well, will it burn or not? Burning is a chemical reaction. So whether something is flammable or not, that is a characteristic, a chemical characteristic. Will it burn or not? The flammability of something. Will it rust? Rusting is a chemical reaction. So whether something will rust or not is a chemical characteristic. We talked about rusting. One you'll see a lot more next year is how acidic or basic, how acidic something is. You'll learn later that's called the pH of a substance. Whether something's very acidic or not is a description of how it could or could not react chemically. These are chemical characteristics. And ultimately, if you want to observe a chemical characteristic, you need to see the substance change chemically. If it starts to burn, or it starts to rust, or it starts to bubble when acid touches it, you can then say these are chemical characteristics. But there's also physical characteristics, things that can, when something changed physically, not chemically, you can get a sense of describing what the substance is based off its physical characteristics. So one is its bendiness, its flexibility. That's a physical characteristic. If you bend something and it breaks, you haven't changed it chemically, but how far you can bend it or not is certainly a physical property of that substance. Is it shiny? Does it reflect light or not? What's its luster? That's kind of a word for shiny or not. That's a physical characteristic. You could observe those physical characteristics without changing it chemically. Some other physical characteristics can be density. We're going to explore density a lot, specifically in this unit. And we could observe what state of matter is the substance is. And the states of matter that we'll see all through, is it a solid, or is it a liquid, or is it a vapor, a gas? The state of matter that the material is in, whatever the substance is, that's a physical property of what it is as well. Now, some properties can kind of change depending on certain aspects of, I guess, the temperature or things like that. But some properties of materials are always the same. and we call those characteristic properties. Characteristic properties are unique properties for specific substances. In fact, characteristic properties are numbers. There are things you can look up, you could Google. For example, the boiling point of a substance is a characteristic property. The boiling point is the temperature at which a liquid becomes a gas. All materials have different boiling points. The boiling point of water, one we'll think about a lot, is 212 degrees Fahrenheit or 100 degrees Celsius. But different materials have different boiling points. Oil will have a different boiling point than water. Gold has a boiling point. At some point, you can have solid gold becomes liquid gold, and if it gets hot enough, it could become gas gold, which is weird to think about because it's a metal, but certainly it is a specific boiling point. You could also have the melting point. This is also a very specific characteristic property. The melting point is the temperature at which a solid becomes a liquid, the temperature at which something starts to melt. And we know that for water, the melting point for water is 32 degrees Fahrenheit. Fahrenheit we use in this country, but in science we have to use Celsius. Thankfully, we have a nice number to remember. It's 0 degrees Celsius. It's kind of annoying. You have to remember 212. It's a hard number to remember. For Fahrenheit, for boiling, 100 degrees Celsius, easy to remember. The melting point of water, 30 degrees Fahrenheit. That's kind of hard to remember, 32. 0 degrees Celsius. Celsius sometimes is easier to remember. Points like this. Now, wait a minute. If the melting point of water is 0 degrees Celsius or 30, well, what's the freezing point? Well, the freezing point is the same thing. The freezing point, as we'll see later on in this unit, and the melting point are the same thing. It's kind of like a door that can go both ways. The door to this classroom, I'm in our classroom right now, and the door to the hallway are the same door. If you're in the hallway, you would describe the door as the door to the science classroom. If you were in the science classroom, you describe the door as the door to the hallway. But it kind of is the same thing. It just depends on whether you're melting or freezing. The point at which that change occurs for water is the same point, 32 degrees Fahrenheit, or as we like to say, 0 degrees Celsius. And finally, and we're going to be looking at these a lot, by the way, throughout this unit, another characteristic property, very specific, is density. And density is the amount of stuff. How much atoms can you put in a certain amount of space? The amount of stuff is the mass. We can measure that with a scale. That's how many atoms there are. And how much space it takes up is we call the volume. That's how much space mass takes up. That ratio of mass to space we call density. And the density of water, let me back this up a little bit. We measure mass in grams, and we measure volume in liters or milliliters. And therefore, the density of water is another number, because remember, densities, all these are specific numbers. The density of water is 1 gram per milliliter. If you have 1 gram of water, it takes up 1 milliliter of space. If you have 10 grams of water, that takes up 10 milliliters of space. The ratio of mass to volume is 1 for density. And in fact, we're going to look at that a little bit further in here with our density. So now we're going to talk just specifically about density. We'll come back to boiling point and melting point a little bit later on. For today's notes, to get up to page 7, we're going to look now just at density. We're going to do a couple little density activities and do some density calculations. So a repeat of what I said before. Density. It's how much mass, how much stuff is in a given amount of volume. And to calculate density, here it comes, we have an equation. The equation to calculate density is this. Density equals mass divided by volume. Sometimes you can think of equations as sentences. This is equals something over something, or something times something. Density is mass divided by volume. And in fact, you don't have to write out the whole word. You can just write D equals M over V. As we see equations throughout the time in 8th grade science, whenever I introduce you to an equation, make a box, put a box around this equation, because you're going to be using this equation a lot. It's always good to know right where we first heard it in our notes. Here's where we'll first hear of the density equation. Density equals mass divided by volume. I'll always give this to you on a quiz or a test. You won't have to memorize it, but if you wanted to, you could think of density equals love. See, it's a heart. Love divided M over V. D equals M over V. Density equals mass over volume. The density of subject does not depend on how much you have. You can have a lot of something, you can have a little something, as long as it's the same substance, it's going to have the same density. And here's an example to kind of put that in perspective. So here's one. Imagine we have water. We already described what the density of water. Imagine we have a cup of water and a huge amount of water, a swimming pool of water. In the cup of water, let's say we have 5 grams of water, and that 5 grams of water take up 5 milliliters of space. 5 divided by 5, that's how we find the density. It's 1, as I said earlier, 1 gram per milliliter. 5 grams taking up 5 milliliters of space. That's the density of water, 1 gram per milliliter. If we have a pool, it would be so much more massive. We'd have so much more water. Let's say we have 5 billion grams of water. That's a lot of water. That's heavy. That's a whole lot of water. But guess what? That water takes up a lot of space. How much space? It takes up 5 billion milliliters of space. 5 billion grams divided by 5 billion milliliters, the math still works out to be the same. It's still 1. You still have just 1 gram per milliliter. All right. So it doesn't matter how much you have. It doesn't matter how much you have, because density is a characteristic property. Whether you have a little bit of water or a big amount of water, the density is always the same. Okay. 2 more other little discussions for the demonstrations that we'll see in here. One is that in terms of floating or sinking, because we know the density of water, if something has a density that's less than water, it will rise to the top. And if something has a density that's greater than water, it will sink to the bottom. And I think we'll do this demo in class. I'll show you this, but you can hear about it. If you have regular Coke and you put it into water, it sinks to the bottom, and Diet Coke floats to the top. They have the same mass. They have the same volume because they have the same size, but there's more sugar in regular Coke because there's more stuff. There's more mass in this can than there is in Diet Coke. It's more dense than water. It sinks to the bottom. More mass means this has a greater density, goes to the bottom. You can also naturally change the density of the material. You can also change the density of the liquid that it may or may not be floating in. If you have ice that's in water, ice cubes, solid ice, will float to the top of water. But if you have ethyl alcohol, a different type of liquid, and you put ice in that, the ice cubes sink to the bottom. So in that example, the ice floats on the water, the ice sinks in the alcohol, and this is because the alcohol is less dense than the ice water, is less dense than water, so that the ice cubes will sink to the bottom. All right, the final page of our notes with this here. So that's another way to kind of think about density. The final way you can kind of put it together with density is to think, one way to think about density is like, how much stuff could you put in a specific amount of space? So how much stuff could you put in a specific amount of space? We can think of it in terms of 3 sort of imaginary scenarios. Imagine we have 3 beakers. I used to do this as a demo, but I think you can get it from these note pages here. And imagine we fill all of them up. The first one we fill with just gravel, and we fill it up to 100 milliliters of space. So the gravel is taking up this amount of space. And the second one we fill up to the same level, same amount of space, but this says gravel and sand together. And this one, we fill it up the same amount of space, take up the same amount of space, but it says gravel, sand, and water. We can do a quick density calculation to compare their densities. So say we look at this one, and we measure it, we put it on a scale, and it has a mass of 200 grams. And I told you that it was filled up to 100 milliliters. So the mass is 200 grams, the volume is 100 milliliters. 200 grams divided by 100, this is how we calculate the density. Density is mass divided by volume. A mass of 200 divided by a volume of 100 milliliters equals 2 grams per milliliter. So in this scenario, the gravel alone in this amount of space is 2 grams per milliliter. Now in that same amount of space, we now add some sand, and the sand sort of fills in some of the openings that in between the pieces of gravel. So now this stuff is getting heavier. In fact, now we say that the mass is 250 grams. 250 grams. There is more mass than we had before. Well, now we calculate the density. Now it's 250 grams divided by 100. 250 grams more mass divided by 100 is 2.5 grams per milliliter. So this is becoming more dense. There's more stuff in this amount of space. Even with sand and gravel in here, there might be little pockets of air. So we pour in the water. the water fills in every little opening that's in there. So now it's got gravel and sand and water. We put it on the scale, and now that we find the mass to be, say, 270 grams, it's getting heavier because now it has some water in it. Now we find the density of the 270 grams divided by 100, and that works out to be 2.7 grams per milliliter. So you can see, as we're putting more and more stuff into the same amount of space, the density goes from 2, and then it gets a little bit bigger to 2.5, and eventually makes it up to 2.7 grams per milliliter. Okay, that was a lot to take in with one set of notes. We're going to be doing both practice problems with density and some density activities involving carrots and apples and some other stuff as well. So as always, let me know if you have any questions. I'm sure you do. We'll hear about this more again in class. We'll go from there. Thanks so much for watching. Add some questions if you have them. Thanks. Bye.